Hello, this is a review of exponent and logarithmic rules. This is section 1.4 and 1.5 from James Stewart Calculus Early Transcendentals. So before you see the various exponent and logarithmic rules you should have learned in an intermediate algebra class or a pre-calculus course. So just running down the list, your first ones in the left-hand column are your general exponent rules. X to the a times x to the b is x to the a plus b. Some examples in there could be if we had x cubed times x squared, that's going to be x to the 3 plus 2, and that's going to be x to the 5th. We could have x to the a over x to the b equal to x to the a minus b. That's going to give us, if we had an example, let's say x cubed over x to the minus 7, that's going to give us x to the 3 minus 7, and that's going to be x to the 3 plus 7, or x to the 10th. If you've got x to the a raised to the bth power, don't forget that an exponent is repeated multiplication of the base. So you would be repeating the multiplication of x times a times x times a to the a times x to the a b times. And then you would be going a plus a plus a plus a from the first rule. And you would get repeated addition, and repeated addition is multiplication. So if we had here x squared raised to the 4th power, that would be x to the 2 times 4, or x to the 8. So you get the idea, and these things should be familiar to you. You will use them an awful lot throughout Calculus 1 and Calculus 2 in your simplifications. So be mindful of them. Remember your negative exponents down here, x to the minus a equal to 1 over x to the a, and if you have a negative exponent in the denominator, you can bring it to the numerator. In other words, this is x to the a over 1. Keep in mind, this is a common mistake that many students make in simplifying expressions in order to integrate. X plus y to the n does not equal x to the n plus y to the n. Remember that an exponent is repeated multiplication of the base. So as an example here, x plus y raised to the 2nd power is x plus y times x plus y. And if you remember how to expand polynomials, you can use the FOIL method in this case, or repeated distributive property, and you get x squared plus 2xy plus y squared, and that is certainly not equal to x squared plus y squared, so be careful about that. And then in this chart we move on to radical rules, which are still exponents themselves. You've got the nth root of x to the n, or the nth root of x is going to be x to the 1 over n. And just remember that in all cases of your radicals, whatever the index is your denominator. So in this case, the nth root of x to the raised to the mth power is going to be, if I've got n as my index, my n is my denominator. Good. So we do have another rule here. The nth root of x to the n is equal to x. You can use the previous rule to demonstrate that, because that would be x to the n raised to the 1 over n, and then we can use a previous exponent rule. That would be x divided, or n to the divided by n, and that would be x to the 1st power, which is x. We also have as a convention, as long as x is not equal to 0, x to the 0 power is equal to 1. We also have some multiplication rules. And this comes from the previous rule of x to the a raised to the bth power is x to the a times b. And also if we have in this other rule right here, if we've got another product in there, that we would raise the exponent to that value. So we can use those two rules to derive the nth root of a times b is the nth root of a times the nth root of b. And the nth root of a divided by b is the nth root of a divided by the nth root of b. These are rules that you should commit to memory and be comfortable using within simplification of algebraic expressions. Now over on the left-hand side, we have some logarithmic rules, and below, after this, I will go over some logarithm and exponential graphs and things. But our log rules are on the right-hand side in this column, and we'll begin with the top. The y equal to log base a of x is equivalent to the expression of a to the y is equal to x. And what I normally point out to students is that a is the base of the log and a is the base of the exponent, and that the log is the exponent, right? The log is the exponent. Good? And so that's how I remember that a log base a of x equal to y is equivalent to a to the yth power is equal to the input value of that logarithmic function. And then we proceed to other log rules. Your log base a of a is equal to 1, and simply it is true because a to the first power is equal to a, and that checks out from the previous rule set. And log base a of 1 is equal to 0, and we see if we convert it to exponent form, we see that a to the 0 is equal to 1, and that checks out as well. You can use exponent rules to derive the properties, and exponent rules and the definition of that y equal to log base a of x to derive the following rules. If we've got log base a of a product, that's going to equal the sum of the logs. And if we have log base a of x divided by y, which is a quotient, that's going to be the difference of the log base a of the top minus the log base a of the bottom. And then finally, another important logarithmic rule, log base a of x to the c is equal to c times log base a of x. And you can see these proofs in a standard pre-calculus book and probably in an intermediate algebra book as well. But it's these three here, this one, and this one, that are going to be extremely useful in differential calculus and calculus 1 when we get to logarithmic differentiation. We also have some buttons on a standard scientific calculator. We'll have an ln button, and we'll also have a log button, so it's important to note what those buttons represent. The log base e of x is known as your natural log, which is the ln of x, and your log base 10 of x is known as your log x. So those are the two buttons that you have on your calculator. That's not to say that you can't use your calculator to solve or to calculate other values of logs, like log base 2 of 8, for example, because you can use the following rule with your calculator if you don't have means to calculate the values exactly. So the log base a of b is going to be the ln of b divided by the ln of a. That is not the ln of b divided by a. It is the value of ln of b divided by the value of ln of a. So be careful about that. You can also use your log button, and it's also equivalent to log of b divided by log of a. Now, what we're going to see in terms of later discussions in this video is that when we have an exponential function, a to the x, its inverse function is going to be log base a of x. And we'll discuss more inverse functions later on, but we also have that inverse functions undo each other, because typically if f sends x to y, then f inverse is going to send y back to x. So we can go through the derivation that if we do a composition of inverse functions, they're going to undo each other. So we get the identity in that sense. So if we have f to the f inverse, or f of f inverse of x, then we're going to just get back x. And if we have f inverse of f of x, we're just going to get back our input value. So that's very useful in simplifying expressions, both in Calculus 1 and Calculus 2. That tells us that the ln of e to the x, since ln of x is log base e, that is the inverse function of e to the x. And so the ln of e to the x is just going to be x. And we also have that e raised to the ln of x is just going to be x. So this one is particularly useful and will come into play often in several examples. So just as further examples there, if we have e to the ln of 7, that's going to be 7. If we have e to the ln of x squared, that's just going to be x squared. If we have e to the ln of sine of x, that's just going to be sine of x. Good, so whatever our input value is, what is going to be that identity. So these are very, very useful rule sets to use as a reference, and I encourage you to do so. All right, so as I mentioned, this is a discussion also on exponential functions and logarithmic functions. So I have here the general graphs of an exponential function. And remember, an exponential function is an f of x equal to a number to the variable x. So I often tell students if x is in the exponent, then we have an exponential function. So our exponential function's here, y equal to f of x, and that's going to be a base e to the x. And that's very different than x to the b or x to the a. If we have x to the a, then we will have either a radical function, a polynomial function, or a rational function if a is negative. So be careful. When the x is in the exponent, that's when you can say that you have an exponential function. So here before you have the graphs of your exponential functions, if we have that b is between 0 and 1, then the graph of the exponential function is above. It is true that 0 is never achieved. It gets awfully close, but it is never achieved if we've got b as a positive number, just based on rules of our exponents. When we have x less than 0, then b to the x is going to be b to a negative number, and that's going to be b to, it was going to end up with a positive output. When x is bigger than 0, b to the x is also positive, and when x is equal to 0, b to the x equals b to the 0, which is going to equal 1. So we will always have an output of 1 no matter what our base value of b is, as we can see over on the right-hand side. But 0 is never achieved, so our line y equal to 0 is a horizontal asymptote. And when your base b is equal to 1, then we don't really have the exponential form. We just have a straight line, because no matter what value of x we have, our output is 1, so we would have a horizontal line when our base is equal to 1. But when we have b is bigger than 1, then we have that traditional exponential form. So what is the domain of a to the x, or domain of b to the x? And remember, a and b can be fixed real numbers. And if we recall that our domain is how wide our graph is, we see that we can put in any real number and we will have a real number output. So the domain of this function is going to be negative infinity to positive infinity, or you can express it as an interval, or you can say that it's the entire set of real numbers. And what is the range of a to the x? The range is how tall your graph is. What are the list of possible output values? And we just discussed that 0 is never achieved, but that we can see from our graphs that we do go to infinity in both cases. So we have that 0 is less than a to the x less than infinity. Infinity is never really achieved, so we use that strict inequality. So we can say that this is or 0 to infinity, or we can say that it is the collection of y where y is strictly bigger than 0. You can say that. All right, So we move on from there just to have those general graphs of exponential functions. You can go to a pre-calculus book or maybe the latter part of an intermediate algebra course and practice using translations of exponential functions, horizontal translations, vertical translations, and flips across the axes and stuff. So then we move on to talk about inverse functions because we want to establish what is the general form of the inverse function of an exponential function. And by the way, both exponential functions and logarithmic functions are transcendental functions, and you'll see why in a second. So in this diagram, so we define our f to the minus 1 to be our inverse function here. F inverse of x is the inverse function of f of x, and it will be a function itself if our original function f of x is 1-to-1. So what does that mean? What does a 1-to-1 function mean? A 1-to-1 function is a function first, right? So a 1-to-1 function, it's a function, so that means it passes the vertical line test. But then also, it passes the horizontal line test. Okay, and what does that mean? So when it's a function, we say it passes vertical line test. And why does it have to pass the vertical line test? Because it validates the definition of a function. For every input value x, there's one and only one output y. If there were two outputs for a single value of x, then we would have 2 points on a vertical line, and your vertical line test would fail. So with your 1-to-1 function, it also passes the horizontal line test. So your 1-to-1 function has to pass the vertical line test, but it also has to pass the horizontal line test. So what does that mean? For every single output y, there's only one x that is associated with it. So in other words, if f of x is equal to f of y, those are two output values, this implies that x is going to have to equal y as well. So we only have one input. So that will guarantee that your inverse function is a function itself. So just backing up as well as another note, please note that it is true that f to the minus 2, or f squared of x does equal f of x squared, but we reserve the minus 1 exponent to denote the inverse function. So f to the minus 1 of x does not equal 1 over f of x. Good? We want to use these definitions over here. Your inverse function is essentially going to undo what your original function did. So in other words, if f sends x to y, then f inverse is going to send y right back to x. It's going to undo it. Good? So this tells us that the domain of your inverse function is going to be the range of your original function, and your range of your inverse function is going to be the domain of your original function because they undo each other. You just swap sets. Good? So we move on to, well, how do we find the inverse function of if we're given a function? So these are our steps. We first replace f of x with y. We can then solve our equation for x, so we're essentially undoing what we did to x. So we solve our function for x, and then we swap x variable for y variable, and then we replace it with the notation of f inverse of x. It is okay to swap step 2 with step 3. Often people will, after they replace f of x with y, they will often interchange x and y and then just solve for y and then replace y with f inverse of x, and that is fine. Good. I move on to also inform the group here that inverse functions, they are collections of points. You can graph that collection of points in the plane, and that's how you can represent a function, by a graph, or you can represent it by its equation. But when f sends x to y, if that means xy is on the graph of f, and f inverse is going to send y back to x, and that means yx is on the graph of f inverse of x. And it turns out, using geometric steps, it can be proven that the graphs of inverse functions are mirror images of each other across the line y equal to x. So these are mirror images. This is the mirror, and these are mirror images across. Oh. So then when we have the graph of y equal to e to the x, which is a very common graph that you should commit to memory, if we were to take a mirror image of that, then this is our standard graph of y equal to ln of x. And remember, 0 was never achieved on the y equal to e to the x, so that means there's no input for 0. So if 0 is never in the range of e to the x, that means 0 is never in the domain of f inverse of x. And if negative x is, or negative value is never in the range of e to the x, that means a negative value is never going to be in the domain of the ln of x. So what is the domain of ln of x? If you see the graph and remember what the graph is, domain, how wide your graph is, then we have that our domain is going to be 0 less than x less than infinity. And our range is going to be from negative infinity to positive infinity. And those are the exact opposite of what we had for e to the x or a to the x. Same thing goes for any base. You have this typical same type of graph. It's just to a different base. So we still would have our 0 to infinity, and here we would still have negative infinity to positive infinity. All right. So just to be clear, if f of x is equal to a to the x, then f inverse of x is going to be log base a of x. Good. And that is in our chart on the very first page. So let's do some examples here of playing with some of the rules, and this might help doing some homework problems. You might see this in a Calculus 2 course, or to evaluate. I tend to use an exponent rule of, I'll tend to take the fraction on the inside and then raise to the 4th power, because I know that 1/3 times 4 is 4/3. And then 8 to the 1/3 is the cube root of 8. And the cube root of 8 is going to give me 2, because 2 to the 3rd power is equal to 8. And then 2 to the 4th power is 2 times 2 times 2 times 2, and that's going to give me 16. Good. Here I'm going to use a series of those exponent rules. At first I'm going to add the numerators. I can, or in the numerator I can combine by adding the exponents. So I can say that this is equal to 2n plus 3n minus 1 divided by x to the n plus 2. And you could actually do it in several different types of steps here. 2n plus 3n is 5n. And now I'm going to use the rule of the difference. If we divide x to the a divided by x to the b, that's going to be f to the x to the 5n minus 1 minus n plus 2. And that's going to give me x to the 5n minus n, which is 4n. And we have minus 1 minus 2, which is minus 3. And then that's it. Down here, just following the steps of taking the inverse. So first I'm going to replace f of x with y. I tend to like to swap spots, so I'm going to swap. I'm going to do step 3 first, and I'm going to say then x here is equal to 4y minus 1 over 2y plus 3. And now I'm going to solve for y. And when I solve for y, I would get x equal to 2y plus 3 equal to 4y minus 1. I'm going to clear my parentheses. And now I'm going to collect the values of y on one side and the values of x on another. And I would get 3x plus 1 equal to 4y minus 2xy. And if I were to factor out my y, I would get 3x plus 1 equal to 4 minus 2x times y. And now I'm going to solve for y, and I would get 3x plus 1 over 4 minus 2x. And finally, I'm going to replace my y with f inverse of x. Oh. Good. One more. If I have ln, I'm going to first rewrite this as y equal to log base e of x plus 3. Again, I'm going to swap my x for my y, and I'm going to say that this is x to log base e of y plus 3. And now I'm going to solve for y. So I'm going to convert to exponent form, and I end up with e to the x is equal to y plus 3. And then I can solve for y, and I get e to the x minus 3. And then finally, I change to f inverse of x, and I get e to the x minus 3, and that is my response. Oh. All right. And then I've got some other problems to use with our table up above. Here it says evaluate without using a calculator. So I'm first going to combine these. I know that this is going to equal log base 10 of 40 times 2.5. And I see that 2.5 is 2.5 and 2.5 is 5/2. So I know that I can cancel my 2 with my 40 to leave 20. And this is going to give me log base 10 of 100. And if I just say that this is equal to x, and I transform this 10 to the what power gives me 100, and I can replace 100 with 10 squared. And because 10 to the x is 1 to 1, because it passes the horizontal line test, then I know that my x here is actually going to equal 2. Good. Same idea over here. If I were just to use without a calculator log base 2 of 32 instead of going log 32 over log 2, I might say let this equal x, and then transform 2 to the x is equal to 32. And then I might say, I might rewrite 32 as 2 to the 5th power. And so that's going to tell me that x here is equal to 5. Same idea here. I might say, let's call this y. Then I can say 5 to the y is equal to 1 over 125. I can rewrite 125 is 5 cubed. I can use my negative exponent rules and say that this is 5 to the negative 3. And now that I have equal bases, because 5 to the x is 1 to 1, I can say that y here is equal to minus 3. Good. Now later on in a differential calculus course, you were more often, when we get to logarithmic differentiation, you're going to want to expand a logarithm instead of making it into a single logarithm. But I'm going to make it into a single logarithm here. So just using some of these rules, I'm just going to, you can do them in any order, but here I go. So with this one, if I've got 1/3, that is a constant, and I can make it an exponent. So this is going to equal ln of x plus 2 cubed to the 1/3 power, and we can use our exponent in there. 3 times 1/3, that's just going to give us x to the ln plus 2. Second, I can distribute my 1/2, so I'm going to go ln of 1/2 of x minus 1/2 of ln of x squared plus 3x plus 2 squared. And I'm going to again use my exponent, my constant, and make it into an exponent inside my radical. So I can say that this is ln of x to the 1/2, and I can say that this is ln of x squared plus 3x plus 2 squared to the 1/2. And again here, that's going to equal 1. So we just have as ln of x plus 2 plus the ln, and I can change this to the square root of x. And here I just have minus ln of x squared plus 3x plus 2. And now I can form with these two, I can combine using the rule for sums. This is going to give me ln of x plus 2 times the square root of x, and I still have minus the ln of x squared plus 3x plus 2. And now I can use my difference and put these guys together and say that this is going to be the ln of x plus 2 times the square root of x over x squared plus 3x plus 2. And it looks like x squared plus 3x plus 2 can be factored. And so I can simplify as much as I can. So if I have x plus 2 times the square root of x over x plus 2 times x plus 1, I know that I can cancel my x plus 2, and I end up finally with ln of the square root of x over x plus 1. And that does it for a basic overview of exponent rules and logarithmic rules and the relationship between exponential functions and logarithmic functions. That does it. Have a great day. I will see you in the